Hey everybody. In this video we're going to start looking at a way to find those coefficients that we were having a look at in the last one. Remember the question marks we had, and it was like, well, we can find out, we can expand these binomials, but the one thing we don't know is the coefficients that go along with it. And we saw some patterns and things like that. Now the method that we're going to use in this video is called Pascal's Triangle to find binomial coefficients. But let me give you a little background on this Pascal character. So this is Pascal. He was a French mathematician back in the 1600s, and so he discovered this method that we're going to use. And you'll find it pretty interesting. But the thing about it is, this guy was apparently he was big on probability. And this, like I said, these binomial coefficients show up in the probability theory. But let me show you the triangle and how it works, and then we'll go back and take a look at Pascal again. Okay, so this is an example of Pascal's triangle. And the way it works is you could start to make your own triangle. You would start with a triangle of ones, just like that. And all the edges are going to be ones every time. Now, every entry other than one is the sum of the two diagonal entries above it. For example, this row here, you would have a 1 on the outsides, but see, this 2 comes from adding those two together. This 3 comes from adding those together. This 3 comes from adding those together, and so on. So you can see how this 4, you sum those two up, and so on and so forth. Now, remember when we had in our original at the top, we had I said, well, where's this 5 and 10 and 10 and 5 and 1 coming from? This arrangement of numbers produces binomial coefficients. Go back up here to this one, you'll see the 1, 5, 10, 10, 5, 1. Okay, so I would call that the n equals 5 row of Pascal's triangle. For example, the n equals 0 row is the 1. Then you got your coefficients of the 1 power, 1, 1, 1, 2, 1, and so on. So when I refer to something as the n equals 5 row or the n equals 7 row, I'm talking about a specific row of the triangle. Okay? So I'm going to compute the n equals 7 row for you, with you, and show you how it works. You always start with a 1, then you sum the numbers above it. 7, 21, 35, 35, 21, 7, and the outer one's always a 1. So that's how you would compute the n equals 7 row of Pascal's triangle. All right, now I gave you an IXL on just doing that. And honestly, I did it myself. It takes about 3 minutes. Not 3, that's an exaggeration. Probably about 10 at most. Okay, so don't look at 2 IXLs and say, well, that's too much. That's an easy one to do. Okay, I want to do a problem with you. All right, so it says using Pascal's triangle to expand a binomial. All right, so here's one that we had earlier. We said, okay, look, we know, and we said we already know how to expand it. We know how to reduce the powers of A, and then it left us the question marks and so on. So what we would do is we would just grab the n equals 7 row, and basically we literally can substitute those for our question marks. And that gives us the full expansion of A plus B to the 7th. All right, so there's our 7, 21, 35, 35, 21, 7 that we just found up here. Okay? Now, it wouldn't be doing you justice for me to leave it at that. Let's use this theorem or this method to do one more. And I said I was going to go back to Pascal in a second, and I will if we get a chance here. Let's see if we can get through this one, and we'll go back and talk about him for just a minute. Okay, so I'm going to expand this binomial using Pascal's triangle. And the first thing I want you to realize is it does fit you got to kind of force it to work. That's 2 is your A. I hate the way it always does that. And negative 3x is your B from the theorem. Okay, so I'm just going to plug this into my theorem and go to work. And I'm going to use the n equals 5 row of Pascal's triangle. So I'm going to grab these. These are going to become my coefficients. And I'm going to need them in just a second. So I'm just going to put them right here where I can see them. and I'm going to go to work. All right, so I'm going to start by, all right, so my a to the 5th is my first term. So you would have 2 raised to the 5th. Right? That's the first thing you have. Plus, well, this has a coefficient there of 5 times 2 to the 4th. All right, times negative 3x to the 1. And remember, these have to sum to 5. Plus, what would we'd have now? 2, or our coefficient first, we'd have a 10, right? 10 times 2 to the 3 negative 3x to the 2. And plus, and just keep working it out like this. Plus 10 again. 2 to the 2 times negative 3x to the 1. Did I mess that up? To the 3, I mean. Because remember, they got to sum to 5. And finally, we're going to get the 5. And I'm getting them from right here. That's where that 5's coming from. 2 to the 1 times negative 3x to the 4, finally, plus b to the 5th, which is negative 3x. I'll see if it'll let me sneak this in. That went to another line. It did. I got lucky. Okay, so that's the expansion in sort of a raw form. Now we need to kind of simplify this because that's not the way this should look. All right, so I'm going to go ahead and fix this up a little bit here, and you may have to take 2 or 3 steps to do this. All right, so that's a 32. We know 2 to the 5th. Okay, now see, these are going to alternate signs because when you have an odd, that's going to be a negative, even, that's going to be a positive, and they'll kind of just take care of themselves if you'll let them. Now I've already computed this here. This 5 times 2 to the 4th times negative 3 gives me a negative 240, and I encourage you to try that on your own. X, and this next one's going to be a positive because I'm squaring that negative 3x, plus 720 x to the 2, and then we get negative 1080 x to the 3 plus 810 x to the 4th, and finally minus 243 x to the 5th. And that is the expansion of that binomial using Pascal's triangle. Oh, what I was going to tell you, there's a Chinese guy, mathematician, that discovered this triangle back in the 1300s. In fact, it was dated back to 1303 before Pascal. So Pascal sort of discovered it second, really, that we know of. There could have been someone before that, honestly. But he gets credit. So they call it Pascal's triangle. And there's a lot of patterns in this triangle. And we could spend a whole lot more time on this. And you might have already noticed that you kind of know the second term too. See that 3 becomes those 3s, that 4 are those 4s. Anyway, play around with this triangle, make some of them. It's an efficient method for small values of n, it turns out. Because here's a couple of questions we need to think about moving forward. I wish I had space there, hold on. The first question I think we need to look at, and you want to think about this, is Pascal's triangle going to be an efficient way to take care of jobs like this one, 3x minus 2 raised to the 25th? You'd have to make a triangle to row 25. I'd like to see you try that. That's going to be a big job. So right away, it's looking like Pascal's triangle has its limitations. For small values of n, it's a fairly efficient method. Another question that we got to kind of look at, we need to be able to answer questions like, what's the middle term in the expansion of 2x plus 1 to the 16th? there's ways to find these things without expanding it all the way out. And there's a way to expand these using a more efficient method for larger powers of n. It really makes a lot of sense. Anyway, that's it for this video, and that's it for the week on these things. So you got an IXL to do with just Pascal's triangle. Then you got to find a couple terms in one. I encourage you to get those things knocked out, because next week we're going to dive right into this with some more methods. Guys, have a great weekend, and I'll see you next week.